So we were discussing what? First order circuits, yes or no? We were discussing first order circuits, and the most important formula is what? That final plus initial minus final times e power minus t by tau, which of course is valid only for first order circuits driven by one or more DC sources, and also this formula assumes that the circuit starts at t equal to 0 and it is valid for t greater than 0. So let's take up one more extremely familiar example of an RC circuit. So look at this. We have R followed by C. Let this RC circuit be driven by a voltage source whose value is what? 10 volts. So is it not a DC voltage source of value 10 volts? And then VC is what? The voltage across the cap. And let us say this circuit starts at t equal to 0. This circuit, it also starts at t equal to 0. But let's say the initial voltage across the cap, it is some 5 volts. So what is VC of 0? It's the initial voltage across the cap. It is how much? It is 5 volts. So given that VC of 0 is what? 5 volts, does it not mean VC of 0 plus is also going to be 5 volts? See, that means what? Before t equal to 0, something happened to the capacitor due to which the capacitor, it got charged to what? 5 volts. So VC of 0 is what? 5 volts. So because VC of 0 is what? 5 volts, VC of 0 plus will also be 5 volts. Okay. What is VC of infinity in this circuit? Because this circuit is being driven by a DC source. At t equal to infinity, it will obviously reach what is called a DC steady state. See, if you recall, I told you whenever any circuit reaches what? DC steady state, all voltages and currents in that circuit will become what? Constant, because DC means what? Anything that remains constant. The voltage will remain constant, current also will remain constant. Okay. So this circuit at t equal to infinity will reach DC steady state. At DC steady state, cap behaves like an open circuit. When the cap becomes an open circuit, this 10 volts will appear across that open circuit. So VC of infinity, everybody knows it is what? Going to be 10 volts. That's all. We have the initial value of VC as what? 5 volts. We also know the final value of VC is what? 10 volts. And of course the time constant is what? R into C. It's a simple RC circuit. So tau is what? RC. And now we can write the expression for VC of t for t greater than 0 using the same formula, which is this: final plus initial minus final times e to the minus t by tau. So here final is what? 10, initial is what? 5, again minus 10 into e power minus t by RC. So this can be written as what? 10 minus 5 e power minus t by RC. So even though we have done this thing several times already, let us again look at the voltage expression from a different viewpoint. If you look at VC of t, 10 minus 5 e power minus t by RC, does it not consist of two parts? It consists of what? Two parts. The first part, what is this first part? 10 volts. Is it not the final value? Remember, final value is what? Value of that current or voltage at steady state. Final value is what? Value of that current or voltage when the circuit reaches what? Steady state. And the circuit reaches steady state after a long time. and after a long time it means what? As t tends to infinity, circuit will reach what? Steady state. So 10 volts is what is called the steady state response. What is this 10 volts called? It is the final value. From now onwards, we will call it as what? The steady state response. Okay. SSR, it means what? Steady state response. Now apart from the 10 volts, in the VC of t expression, there is also one more part, which is this 5 e power minus t by RC, or you can say it is what? Minus 5 e power minus t by RC. Is it not the, natural, not natural, if you look at this part of the response, does it not decay with time? Yes or no? Whereas this part remains constant. It should remain constant because it's steady state. All voltage and currents will become what? Constant, because the source is what? DC. How will you decide what kind of steady state will be attained by the circuit? It completely depends on the nature of the source. So what will decide the nature of the steady state response? The nature of the source will decide the nature of the steady state response. So in this circuit, the source is what? DC. So obviously it will reach what? DC steady state. If the same source is what? AC. Yes, if the RC circuit is driven by, let's say, a sinusoidal voltage source, then it will reach what is called AC steady state or sinusoidal steady state. But right now, source is what? DC. It reaches DC steady state, and at DC steady state, the voltage will be what? Constant, or it does not change with time. Here also, the steady state response is what? 10, which is independent of time, or it remains what? Constant. But apart from the 10 in the response, that is what? VC of t, we also have a time varying part. In fact, is it not a decaying exponential? Yes, look at the other part of the response, minus 5 times e power minus t by RC. In fact, the other part is what? Minus 5 e power minus t by RC. Clearly, this part of the response will exponentially decay with time. Yes, and after a long time, this exponential will decay to what? 0. Then minus 5 into 0, it becomes what? 0. Then what will be left? After a long time, only the steady state response will be left. So before reaching steady state, whatever the circuit does is what is called the transient part of the response. You understood? So from now onwards, any circuit that has at least one energy storage element, listen to this very carefully, any circuit that has at least one energy storage element, that means at least one capacitor or at least one inductor driven by a DC source or an AC source, will always consist of two parts. Response means what? Any voltage or any current of interest in that particular circuit as a function of time will consist of two parts. One is what? The steady state response. The other part is what? The transient response, which will in general decay with time. So always the transient response will decay with time, so that after a long time the transient will completely decay to what? 0. Only the steady state response will persist, or it will remain at steady state. Okay. So what is this decaying part of the response called? Transient response. And in general, the transient response will always consist of a decaying exponential. Only then the transient response will decay to what? 0. If the transient response contains what? A rising exponential, that means what? The transient will not decay to 0. It will shoot up to what? Infinity, meaning the circuit is what? Unstable, or the system is what? Unstable. Any system, if it is what? Stable, the transient response of that system will eventually decay to what? 0. Is this point clear? If any system is what? Stable, then its transient response will eventually decay to what? 0. Here also, look at the transient part of the response, minus 5 times e power minus t by RC, which will exponentially decay to what? 0. I hope it is clear. But if the same circuit, not this circuit, if some other circuit is what? unstable, then the transient response, instead of decaying to 0, it will blow up to what? Infinity. It will exponentially rise and eventually go to what? Infinity. And that is when the circuit or the system is what? Unstable. Okay. Anyway, the bottom line of this small discussion is what? Always the complete response. This Vc of t is what? The complete response. So CR means what? Complete response. SSR means what? Steady state response. TR means what? Transient response. This is true for any circuit containing at least one energy storage element. Always the total or the complete response will consist of two parts. The steady state response, which will remain at steady state, plus the transient response, which will decay to 0 ultimately. But initially, transient will also be there along with the steady state response. After a long time, transient will decay towards 0. Only the steady state part of the response will remain. That is after a long time. You understood? Yes. Now there is one more terminology for the same two responses, namely the steady state response and the transient response. You see, I already told you the steady state response will depend on the type of source that is connected to the circuit. Right now source is what? DC. It reaches what? DC steady state. So can we not say the steady state response is being forced by the input source? I'll say it again. The steady state response is being forced by the input source. You understood? Because the steady state response is a direct function of the input source, it is as if the steady state response is what? Being forced by the input source. So the other name for steady state response, anybody? Please type in the chat box. I'm saying what? Steady state response is being forced by the input source. Input source DC. Steady state response is also what? DC. Forced response. Very good. Excellent. So steady state response, because it depends on the input source or it is being forced by the input source, it is also called as what? The forced response. Okay. What is the other name for the transient response? You see, the fact of the matter is what? The nature of the transient response. Nature of the transient response, it only depends on the nature of the circuit and not the source. I'll say it again. This is an extremely important statement, almost like a golden statement. I'll say it again. The nature of the transient response. Nature of the transient response, it only depends on the nature of the circuit, not the type of source driving the circuit. Whether source is what? DC or AC or any kind of ramp or whatever. Yes, the nature of the transient response or the form of the transient response, it only depends on the nature of the circuit. So here 2 points. Let me go to the next slide and write it. These 2 points are extremely important. SSR, that is what? Steady state response depends on the nature of the source. The other part of the response, that is what? Transient response. The nature of the transient response, it only depends on nature of the circuit but not the nature of the source. Nature of the TR, that is what? Transient response, depends on the nature of the circuit, nature of the transient response depends on the nature of the circuit and not and does not depend on the nature of the source. So when I say nature of the circuit, what does it exactly mean? Nature of the circuit means what? What elements are present in the circuit and how they are connected. Only that will decide the nature of the transient response. Okay, for example, in our circuit, because it's an RC circuit will have a particular form of what? Transient response. Similarly, RL circuit and RC circuit both are what? First order circuits. In fact, all first order circuits will have a particular type of transient response. In the same way, all second order circuits will consist of a particular type of transient response. All third order circuits will consist of a particular type of transient response. So transient response, it depends on the nature of the circuit but not on the nature of the source. Because the transient response, it only depends on the nature of the circuit, transient response is also called as natural response. So what is the other name? What is the other name for transient response? Because it depends only on the nature of the circuit and not on the nature of the source. From now onwards, we will be calling the transient response as what? Natural response. Transient response will be called as what? Natural response. Okay. So earlier we wrote what? The complete response of any circuit containing at least one energy storage element will consist of two parts, namely the steady state response and the transient response. Now because the steady state response depends on the nature of the source, the input source is also called the forcing function. The other name for the input source is what? The forcing function. So steady state response is also called as what? The forced response, whereas the transient response is also called as what? Natural response. Yes. So in fact, this natural response or the transient response, already we know, will it remain forever or will it eventually decay to zero? Always natural response or the transient response, it will eventually decay to what? Zero. And because it will eventually decay to zero, always the transient or the natural response will consist of some number of decaying exponentials. In fact, the number of decaying exponentials in the natural or the transient response is directly related to what? The order of the circuit. I'll say it again. The number of decaying exponentials in the transient or the natural response is directly related to what? The order of the circuit. What was our circuit? Was it not a first order circuit? And in the first order circuit or in the transient response or the natural response of the first order circuit, how many decaying exponentials we had? We had only one decaying exponential. So if you have a second order circuit which is stable, then the transient or the natural response will consist of two decaying exponentials. And if it's a third order circuit, then again the transient or the natural response will consist of what? Three decaying exponentials. But along with the transient or the natural response, we will also have the steady state or the forced response, and the sum of these two will be what? The complete or the total response. You understood? Yes. Okay. So now the point is what? Natural response will consist of one or more decaying exponentials depending on the order of the circuit, whether it is first, a second, a third order circuit and so on. Okay. Now what exactly is that natural response, or what exactly is that decaying exponential which is part of the natural response? See, always the natural response will be what? Some a times e power st. A times e power st. What is this s? This s is what? The pole of the circuit. S is what? The pole of the circuit. So in the natural response, how many exponentials are there? There is only one exponential. So this is what? Natural response of a first order circuit. This is what? The natural response of a first order circuit. Had it been a second order circuit, then in the natural response, you are going to have two decaying exponentials. But right now, we are only looking at a first order circuit. So the natural response will consist of only one decaying exponential. And the general form of the natural response of a first order circuit is what? A times e power st, where s is what? The pole of the circuit. Now the question is, how do you find the pole of the circuit? First of all, for a first order circuit, always the pole is equal to what? For a first order circuit, can you tell me what is the location of the pole in the S plane or in the complex plane? Please type in the chart box. What's the relation between the pole location and the time constant? Any first order circuit, is it not characterized by a time constant tau, which is either equivalent to what? R equivalent into C equivalent or L equivalent by R equivalent. Please type in the chart box. What is the relation between the pole location and the time constant? What's the relation between pole location and the time constant? Please type in the chart box. Relation between pole location and time constant. Minus 1 by t. Very good. Okay, it is not just inversely proportional. It is proportional to 1 by tau, but the pole will lie in the left half plane. Yes or no? Pole will lie in the left half plane. So always the pole location will be equal to what? Minus 1 by tau. Pole location will be equal to what? Minus 1 by tau. And in general, tau is what? Positive. In general, tau is what? Positive. Because it is a product of resistance and capacitance. You can also have a circuit which will have a negative time constant. Anyway, let's say tau is what? Positive, which is true in most of the cases. If tau is positive, tau, will it not be positive real? Tau is what? Positive real. R into C. R is what? Resistance real. C is what? Capacitance, that is also real. So tau is what? Positive real. So minus 1 by tau, is it not negative real? Minus 1 by tau, it is what? Negative real. So if I have to show this pole on the complex plane, this is what? The complex plane. This is the imaginary axis. This is what? The real axis. So where does the pole lie? Where does the pole lie? Where does the pole lie? Please type in the chart box. Where does this minus 1 by tau lie? Does it not lie on the negative real axis? Left half, that's for sure, but it will lie where? On the negative real axis, because what is the pole location? Minus 1 by tau. It is what? Negative real. So it will lie on the negative real axis. Yes or no? This is what? The pole location, which is minus 1 by tau. You understood? Yes. So this is the pole location of a first order circuit. For a first order circuit, first of all, we know there will be what, a time constant. For any first order circuit there will be a time constant, and the pole location is equal to what, minus 1 by that time constant. Okay. Now what is the way to get the poles of any given circuit? How do you find the poles of any given circuit? Okay, first order circuit, already we can use this result, but how do you get this result actually? See, so if you are given any circuit, first you make it source free. If you are given any circuit, you make it what, source free. Usually our RC circuit will be driven by what, a source. So that source I made it 0. That source I made it 0. When I make that source 0, let this be R, let this be C. Let Vc be the voltage across the cap. Let this current be I. I is what, C dVc by dt. And what is this? Let it be VR. So VR is what? The drop across the resistor. Vc is what? The drop across the capacitor. And if you write KVL around the loop, minus connected what, plus, won't we get VR plus Vc equal to what? 0. We will get VR plus Vc equal to what? 0. VR is what? I into R plus Vc equal to what? 0. Now I, it is also what, the current through the capacitor, which is C dVc by dt. So in place of I, if you write C dVc by dt, won't you get RC dVc by dt plus Vc equal to what? 0. RC dVc by dt plus Vc equal to what? 0. Already we know this equation. This is the differential equation governing this source free RC circuit. This is what, the differential equation governing this source free RC circuit. RC dVc by dt plus Vc equal to 0. Is it not a linear first order homogeneous differential equation? It is what? A linear first order homogeneous differential equation. And it is also what? An ordinary differential equation. So what is that equation? RC dVc by dt plus Vc equal to what? 0. You see the general solution for this linear first order homogeneous differential equation will be some type of exponential. Will be some type of what? Exponential. So let's assume Vc is what? Some a times e power st. Vc is what? A times e power st. If Vc is what? The solution that is assumed, this a times e power st is what? The solution assumed for this differential equation. A times e power st is what? The solution that we are assuming for this differential equation. If Vc is what? A times e power st, what is dVc by dt? Is it not As times e power st? dVc by dt is what? As times e power st. Now go back to the differential equation. If you go back to the differential equation, because we are assuming a times e power st to be the solution of this differential equation, in place of Vc you write a times e power st. In place of dVc by dt you write what? As times e power st. Look at this. First you have RC, then dVc by dt is what? As times e power st, and then plus Vc. Vc is what? A times e power st, and this sum, it is what? 0. Now what is common to the two terms on the left hand side? Is it not a times e power st? If you take out a times e power st, won't you get RCS plus 1 equal to 0? If you take out a times e power st as what? Common, then the equation becomes what? A times e power st times RCS plus 1 equal to what? 0. See, we are assuming a times e power st to be the solution of our differential equation. And if the cap is what? Initially charged to some voltage, then it will take some time for the cap to get discharged through the resistance on. So Vc is not going to be 0, and this Vc, it is not going to be 0. That means a times e power st, that is what the solution of this differential equation, it is not 0. We are not interested in a 0 solution. We are interested in a non-zero solution to this differential equation. That means a times e power st is not 0. If this is not 0, but left hand side must be what? 0. Given that a times e power st is not 0, how will the left hand side become 0? Is it not when this factor becomes 0? Yes or no? Given that a times e power st, which is nothing but Vc, cannot be 0, then the only way the left hand side of this equation will be 0 is when RCS plus 1 becomes what? 0. So now we get the very important equation, RCS plus 1 equal to what? 0. Please type in the chart box, what is this equation called? What is this equation called? Please type in the chart box, what is this equation called? Okay, Pooja says it is characteristic equation, very good. Others also, what do you think? Is it not the characteristic equation? So this RCS plus 1 equal to 0 is what is called the characteristic equation of the system or the circuit. So this is called as what? Characteristic equation. CE stands for what? Characteristic equation. What is this characteristic equation? RCS plus 1 equal to what? 0. Now RCS plus 1 equal to 0. What is S? Is it not minus 1 by RC? So what do the roots of the characteristic equation tell you? What are the roots of the characteristic equation called? Please type in the chart box. Roots of the characteristic equation are what? Or what are the roots of the characteristic equation called as? Poles. Roots of the characteristic equation are nothing but the poles of the system. So if you look at this characteristic equation, what is the only root? S is what? Minus 1 by RC. S is what? Minus 1 by RC. What is RC for us? In our RC circuit, RC is what? Time constant. So that is why previously we directly wrote that the pole will be at minus 1 by tau and not 1 by tau. You understood? Yes. So S is equal to what? Minus 1 by tau. So how do you get the poles of the circuit? How do you get poles of the circuit? You should set up the characteristic equation. You should get the characteristic equation, and then the roots of the characteristic equation are nothing but the poles of the system. Why are the poles of any system very important? Please type in the chart box. What exactly will the poles of any system decide? What exactly the poles of any system are going to decide? Or why are poles important for any system? Okay, system stability. Okay. What else will they decide apart from system stability? Please think in the context of the current discussion. Transient response, that's correct. Poles will decide transient response. Of course, poles also will decide whether or not the system is going to be stable when you apply what? Bounded input and so on. But the poles will decide what? The transient response, because what is the nature of the transient response? A times e power st. This is for a first order circuit, and only if the pole is what? Negative real, that transient response, will it not become a into e power minus t by tau, and then it becomes what? A decaying exponential. You understood? So poles of any circuit will decide what? The transient or the natural response of that circuit. Okay? And how do you get the poles of any system? First you get the differential equation governing the circuit by making all the independent sources zero. Listen carefully. How do you find the poles of any system? First you form the differential equation governing the circuit by making all the independent sources zero. Once you get the differential equation governing the circuit, which is going to be a linear homogeneous differential equation, assume the following solution to that differential equation. Assume this solution to that differential equation, which is what? Homogeneous. And what is a differential equation solution? A times e power st. So if you assume this solution for the differential equation, and if you put this solution back into the differential equation, then a times e power st will come out. Then you will get the polynomial, and that polynomial as a function of s should be equated to what? 0. So when you equate this polynomial to what? 0, then you get what is called the characteristic equation. In fact, all linear circuits will have a transfer function. Transfer function is what? A numerator polynomial n of s divided by the denominator polynomial d of s. And when you equate d of s, that is what? Denominator polynomial, to 0, you will get the exact same characteristic equation. So this is something you must be already knowing. So denominator polynomial of the transfer function equated to 0 will give you what? The characteristic equation. But here, without writing any transfer function, directly we are writing the what? Characteristic equation. So for that, what did we do? First we make all the independent sources 0. Please try to remember this. Make the independent sources 0. Then you try to form the differential equation for that source free circuit. It could be first order or second order or any order. Then in the differential equation, or for the differential equation, you assume a solution of the form a times e power st, and put that solution into the differential equation. Then you will get the same a times e power st, which is the solution that has been assumed for the differential equation, times a polynomial in s equal to what? 0. And this polynomial must be equal to what? 0, to get the characteristic equation. And the roots of the characteristic equation are nothing but the poles of the circuit or the system. And why are the poles important? As you all said, poles will decide what? The transient or the natural response. I hope it is clear. So poles will decide what? The transient or the natural response. As you can see here, pole of a RC circuit, it is equal to what? Minus 1 by tau, which is what? Negative real. So it will lie on the negative real axis. So the transient response will consist of one decaying exponential. So if you go back, I told you what? Natural response or the transient response of a first order circuit will be what? A times e power st, where s is what? The pole of the circuit. So in place of s, which is what? The pole of the circuit, can't we write minus 1 by tau or minus 1 by RC, so that the natural response will become what? A into e power minus t by tau. Okay. So in the very beginning of this session, we took this simple circuit example where we had an RC network driven by a 10 volt DC source, and the initial voltage across the cap has been assumed to be 5 volts. And if you look at the complete response, it is what? 10 minus 5 e power minus t by RC. How did we get to this expression? By using the formula final plus initial minus final times e power minus t by tau. Now this final initial formula is valid only for first order circuits, that too when the source is what? DC. If the same first order circuit is driven by an AC source, then you cannot use this final plus initial minus formula. You understood? If the same first order circuit is driven by a source which is not DC, for example AC, please do not use this final initial formula. So in that case, how will you proceed? Or let's say the circuit is not first order, let it be second order. If it's a second order circuit, then how will you find the complete response? Definitely you can't go by this final initial formula. We have to follow the general approach, which is what? The complete response is equal to what? The steady state response plus the transient response, or the forced response plus the natural response. And to write down the form of the natural response, you should know the poles of the system. And to find the poles of the system, you should form the characteristic equation of the system. And to form the characteristic equation of the system, you should form the differential equation governing the circuit. From the differential equation, by assuming the solution to be what? Some A times e power st, we get the characteristic equation. From characteristic equation, we get what? Poles. From poles, we get what? Natural response. And to the natural response, we always add what? The forced or the steady state response to get the complete response. And in the complete response, there will be one or two unknowns. In fact, in the natural response, what was that natural response? Is it not A times e power st? Yes or no? So natural response is what? A times e power st. Okay, S is what? The pole of the circuit, which we already know is what? Minus 1 by tau. Now still A has to be found. So how do you find the value of A? By using the initial conditions in the circuit. What are the two initial conditions possible in any circuit? One is what? The initial voltage across the cap. The other one is what? The initial current through the inductor. So using the two initial conditions, one on the cap, another on the inductor, we can find the value of A. But before you find the value of A, you should add the steady state or the forced response to the natural response to get the complete response. Then you start using the initial conditions to solve for unknowns like, this A. I hope this method is clear. Okay. So what I will do for the same circuit, I will just demonstrate the alternate approach that we will be going to follow from now onwards, especially for second order circuits and also circuits driven by AC sources. Yes, final initial will be followed for first order circuits driven by DC sources, but for analyzing second order circuits and also analyzing any circuit driven by AC sources, we will be following this second approach. Once again, RC circuit driven by a 10 volt source. Just like in the previous example, VC of 0 is what? 5. Now also VC of 0 is what? 5. So it is what? A first order circuit. First order circuit, the natural response will consist of how many exponentials? Only one decaying exponential. In fact, Vc of t will be what? SSR plus TR. SSR is also called as what? FR. TR is also called as what? NR. What is the steady state response? It is the value of Vc at steady state. Steady state response is always what? Value of Vc at steady state. Let me write it. So steady state response is what? Value of that current or voltage at steady state. In this case, we are finding what? Vc of t. So steady state response is what? Vc of infinity. Because the source is what? DC, it reaches what? DC steady state. 10 volts will appear across the capacitor, which becomes what? Open at DC steady state. So Vc of infinity is what? 10. So the steady state or the forced response is what? 10. Now the natural response, which we already know is what? A times e power st. A times e power st, where S is what? The pole of the RC circuit, which is minus 1 by RC. S is what? The pole location. And for the RC circuit, what is the pole location? Minus 1 by tau. So A times e power minus t by tau. You understood? That's all. This is Vc of t. Now what is the only unknown in the expression for Vc of t? Is it not a? It is what? A. So now to find the value of a, you should use the given initial condition. Just substitute t equal to what? 0. Vc of 0 is what? 10 plus, if you put t equal to 0, e power 0 is what? 1. Is it not 10 plus a? And the given initial condition for the cap is what? 5. So 10 plus a equal to what? 5. 10 plus a equal to 5. A is what? Minus 5. If a is what? Minus 5. Now come back to the expression for Vc of t. First term is what? 10, which is the forced response. The second term is what? A times e power minus t by tau, which is the decaying part of the response or the transient response, and a is what? Minus 5. So if in place of a, if you write minus 5, won't you get the exact same result that we got previously by using what? Final initial formula, 10 minus 5 e power minus t by tau. Let me write RC in place of tau. Is it clear, this approach? So from now onwards, the complete response will be equal to what? The forced or the steady state response plus the natural or the transient response. Forced response is what? Very obvious. It is just the value of the current or voltage at t equal to what? Infinity, when it reaches what? Steady state. And what will decide the nature of the steady state? The source will decide the nature of the steady state. Source DC, circuit reaches DC steady state. Source AC, circuit reaches what? AC steady state. In fact, after a couple of days, we will get started with AC analysis. There we will look at AC steady state, but for now it is only what? DC steady state. At DC steady state, cap is what? Open, inductor is what? Short. And to the forced response, you should add what? The natural or the transient response, which will consist of one or more decaying exponentials depending on the order of the circuit. First order, 1 decaying exponential, second order 2 decaying exponentials, third order 3 decaying exponentials, and so on. And for a stable circuit, all exponentials will eventually decay to what? 0, so that only the steady state response will be left. I hope this discussion is what? Clear.